welcome to the deep dive. Today, we're jumping into two really fascinating sections of the periodic table, the D block and the F block elements. Our main source for this exploration is leech104.pdf, which is, well, pretty dense with information on their electrons, properties, and why they're important.
Exactly. And our goal today is sort of to give you the essential rundown. What makes these transition metals the D block and the inner transition metals the F block tick.
Right.
We'll look at where they sit on the table, their key features, and, why they show up so much in the world around us.
So the mission is to get the core ideas, the sort of aha moments, without getting lost in all the super technical jargon.
Precisely. A quick grasp of the fundamentals.
Okay, let's dive straight into the D block then. These are the transition metals, sitting right there in the middle, groups 3 to 12.
Yep, sandwiched between the S block and the P block, they form that bridge.
And what really defines them is how their d orbitals get filled up with electrons, right?
That's the key. It happens across 4 long periods. You've got the third series, scandium to zinc.
Okay.
Then the Ford, yttrium to cadmium. The 5B includes lanthanum, then hafnium through to mercury.
And the last one.
And the 6D series starts with actinium, then rutherfordium over to copernicium.
And that name, transition metals, it actually means something, doesn't it? It's not just random.
Not at all. Originally, it was because their chemical properties seemed, well, transitional, bridging the gap between those very metallic SEP block elements and the more covalent PU block ones.
Blood sense.
The modern definition from IUPAC is a bit more precise. It focuses on the electrons. They're metals with an incomplete D subshell, either as a neutral atom or in their ions.
Ah, but there's a little catch there, isn't there? What about group 12? Zinc, cadmium, mercury.
Good point. They actually have a full D10 configuration, so technically...
They don't quite fit the strict definition.
Exactly. They aren't transition metals by that IUPAC rule. But because they sit at the end of those D block rows, their chemistry is closely linked, and we usually study them together.
Fair enough. So it all comes back to those electron configurations. What's the general pattern there?
Generally, the outer configuration looks like N1D 1 to 10's 1 or 2. So the d orbitals being filled are actually in the shell inside the outermost shell.
Okay, N1D and Ns.
But chemistry loves exceptions. The energy gap between those N1D and N orbitals is often really small.
Right.
Which leads to some electron shuffling for stability.
Like chromium and copper. Those are the classic examples everyone learns.
Exactly. Chromium goes for 35 4s 1 instead of 34 4s 2, and copper prefers 30-10 4s 1 over 39 4s 2.
Why do they do that?
It really boils down to stability. Having a half-filled D subshell like D5 or a completely filled one, D10, is just a more stable, lower energy state.
Oh, okay. Nature finding the most stable arrangement.
Precisely. And for zinc, cadmium, mercury, and copernicium, that group 12 again, they stick to the pattern. N1D10, Ns2, nice and full.
Okay, location electron setup, checked. Now what about their general characteristics? What are these D block elements like?
Oh, they are very typically metallic. High tensile strength, meaning they're strong.
Right.
They're ductile, you can draw them into wires. Malleable, you can hammer them into sheets.
Worse.
And they're great conductors of heat and electricity. Plus, they have that characteristic metallic luster that shines.
So strong, shiny, conductive. What else stands out?
Generally, they're very hard, and they don't evaporate easily, low volatility, although zinc, cadmium, mercury, and manganese are a bit softer or more volatile than the others.
Interesting exceptions.
And their melting and boiling points are usually very high.
Why is that?
It's because both the outer N's electrons and those inner N1D electrons get involved in the metallic bonding between atoms.
So more electrons participating means stronger bonds.
Exactly. More glue holding the atoms together. It takes a lot of energy to melt or boil them. You see a peak in melting points, usually around the middle of each series, near the D5 configuration.
But you mentioned some anomalies.
Yeah, manganese and technetium kind of dip unexpectedly in that trend. Still high, but lower than their neighbors.
And this strong bonding, that must mean it takes a lot of energy just to pull the atoms apart in the solid state, too.
Absolutely. That's reflected in their high enthalpies of atomization. That's the energy needed to turn the solid metal into individual gas atoms.
Like a measure of how sticky the atoms are to each other.
A good way to put it. And again, the highest values tend to be around the middle of each series. Strong interatomic forces.
Okay.
What's quite interesting is that the elements in the second and third rows, the Ford and 5-bed series, generally have higher enthalpies of atomization than the first row, the third series.
Really? Why is that?
It indicates even stronger bonding between those heavier atoms. This actually contributes to why they are more prone to forming direct metal-to-metal bonds in some of their compounds.
Fascinating. Okay, let's talk size. Atomic and ionic radii. What happens as we go across a series?
Generally, for ions of the same charge, say M2+, the radius tends to decrease as you move from left to right across the series.
Why the decrease?
Well, you're adding protons to the nucleus, so the positive charge increases. This pulls the electrons in more tightly.
But you're adding electrons too.
You are, but they're going into those d orbitals, and d electrons are, well, they're not great at shielding the outer electrons from that increasing nuclear charge. The view of the nucleus isn't blocked very well.
Ah, ineffective shielding.
Yeah.
So the pull wins out.
Exactly. The effective nuclear charge increases, shrinking the ion. A similar, though maybe less dramatic, trend happens with the neutral atoms, too.
Now, I remember something about the sizes down a group being a bit weird here. Like, the third row elements aren't much bigger than the second row.
You remembered it correctly. That's a really key point. As you go from the third series to the 4D series, the atoms get bigger, as you'd expect.
Standard periodic trend.
Right. But when you go from the Ford series to the 5D series, the atomic radii are surprisingly similar, sometimes almost identical.
Why doesn't it follow the usual bigger as you go down rule?
It's because of something called the lanthanoid contraction.
Okay, sounds important. What is it?
Before you get to the 5D elements, you have to fill the 4f orbitals. That's the lanthanoid series tucked away at the bottom.
Right.
Now, f electrons are even worse at shielding than d electrons. So as the nuclear charge builds up across the lanthanoids, there's a significant decrease in atomic size.
So the lanthanoids themselves are shrinking.
Considerably. By the time you get back to the d block to start the 5D series, elements like hafnium are starting off much smaller than you'd otherwise predict.
And that shrinkage counteracts the expected size increase from going down a group.
Exactly. It pulls the sizes of the 5D elements back down, making them very similar to their 4D counterparts above them.
Wow. Any classic examples?
Zirconium, ZR in the 4D series, and hafnium, HF, right below it in the 5D series. Their radii are almost identical.
And that has chemical consequences.
Big time. Their chemical properties are incredibly similar because their sizes are so alike. It makes separating them a real challenge. They often occur together in nature.
Okay, that lanthanoid contraction is a major factor then. Let's shift to ionization enthalpies, the energy needed to remove electrons. What's the trend there?
Generally, moving across the series, the ionization enthalpy increases.
Makes sense. Stronger pull from the nucleus.
Right. But the increase isn't as steep or dramatic as you see for, say, main group elements when you remove successive electrons. It's a more gradual climb to pull off the second or third electron.
And the first ionization enthalpy, is it smooth?
Not always perfectly smooth. There are some irregularities. Removing that first electron can slightly change the relative energies of the 4s and 3rd orbitals, which adds a bit of unpredictability.
And which electrons get removed first when they form ions?
Always the outermost nth electrons. Even though the N1d orbitals are filled after the n orbital in terms of energy level order for neutral atoms, when you form a positive ion, the nth electrons are lost first.
Okay, outermost first. Got it.
Yeah.
You mentioned stability playing a role again, especially for second and third ionizations.
Yes, definitely. You often see little jumps or deviations in the trends when removing an electron results in a particularly stable configuration.
Like the half-filled or fully filled ones.
Exactly. Think MO, which has a stable day configuration, or FIO, also day. Losing an electron to reach that state might be easier, or losing another from that state might be harder.
And this stability is linked to exchange energy. Hund's rule.
Precisely. Exchange energy is a quantum mechanical effect that adds extra stability when you have multiple electrons with the same spin in different orbitals of the same subshell, like in DO or DO configurations. Hund's rule tells us electrons prefer to occupy separate orbitals with parallel spins first, maximizing this exchange energy.
Okay, stability is key. Now let's talk about one of the defining features. Their variable oxidation states. Why can they have so many different charges?
That's a hallmark, isn't it? It's largely because the energies of the N1d and Ns electrons are very close.
So different numbers of electrons can participate in bonding relatively easily.
Exactly. It doesn't cost a huge amount of energy to involve slightly more or fewer d electrons along with the s electrons.
Who shows the most variety?
Usually the elements smack in the middle of the series. Manganese is the classic example, showing every state from +2 up to +7.
And at the ends?
Fewer options. At the beginning, like scandium or titanium, there just aren't that many valence electrons to lose or share. At the end, like Copper or zinc, the d orbitals are nearly or completely full, making it harder to achieve very high positive states.
So the maximum oxidation state often relates to the group number, up to a point.
Yes, up to manganese, the highest common oxidation state often equals the sum of the s and d valence electrons. Beyond Mn, the higher states become less stable.
Another interesting point is that their states often differ by just one unit, right? Like +2, +3, +4.
That's right. Unlike main group elements where you often see jumps of 2, like 10 plus 2 and plus 4, transition metals commonly show consecutive states.
What about trends going down a group? Is it like the p block, where heavier elements prefer lower states, the inert pair effect?
Interestingly, often the opposite, especially in the middle groups, say 4 through 10.
Really? Heavier ones like higher states?
Often, yes.
Huh.
For example, in group 6, molybdenum and tungstens are quite stable, whereas chromium is a very strong oxidizing agent.
Mm-hmm.
Think of dichromate, chromin over a douche.
Right, that's a common lab oxidant, but molybdenum aren't like that.
No, they're much less oxidizing. It's a reversal of the p-block trend.
That's counterintuitive but important, and sometimes they can have really low, even zero oxidation states. How does that work?
Yes, in certain compounds, especially with ligands like carbon monoxide, CO, these ligands are good at not only donating electrons to the metal, forming a sigma bond, but also accepting electron density back from the metal's d orbitals into their own empty orbitals. Pi backbounding.
So it's a two-way electron flow.
Exactly. This stabilizes the metal even when it has a very low or even zero formal charge. Think of nickel carbonyl, NiSo, or iron pentacarbonyl, FeOso. The metal is formally zero valent.
Wow. And just to note, scandium is a bit of an outlier here. It doesn't really do the variable oxidation state thing.
Correct. Scandium almost exclusively forms SCO.
Okay, ligands can really change the game. Let's connect this to their behavior and solution standard electrode potentials, EGRI values.
Right. These tell us about the tendency of a metal to be oxidized or reduced in solution. For the MRM potential in the third series, there's a general trend towards becoming less negative or more positive as you go across.
Less negative means harder to oxidize the metal.
Generally, yes. It reflects the increasing ionization enthalpies. It's getting harder to pull those electrons off.
But there are bumps in that road, too. You mentioned Mn, Ni.
Yes, Mne and Zn have E values that are more negative than the general trend suggests.
And there are specific reasons.
For manganese and zinc, it ties back to the stability of their ions. Ma is dine, Ziora is di. Forming these stable ions is relatively favorable.
And nickel.
For nickel, the neon ion has a very high hydration enthalpy. It loves being surrounded by water molecules, which makes forming the ion in solution energetically easier than expected.
What about copper? Its potential is positive.
Right. ECRO is positive. That's why copper metal won't react with simple acids like HCl to produce hydrogen gas.
It doesn't want to become Kuyo in solution.
It's energetically uphill. Copper atoms are held tightly in the metal, high atomization energy, and the energy released when Q is hydrated isn't enough to compensate for the energy needed to form the ion in the first place.
Okay, what about the MO potentials? What do they tell us?
These reveal the relative stability of the +2 versus the +3 state. Again, electron configurations are key. Scandium's value is very low because SCO, noble gas configuration, is extremely stable compared to SCO.
And zinc.
Zinc's value is very high because removing a third electron from the stable Da configuration of Zna is incredibly difficult.
What about manganese and iron?
The value for Mna is quite high and positive. This tells us Mna is a strong oxidizing agent because it readily accepts an electron to become the stable Dao.
Okay.
Conversely, the Fe-Fe potential is lower. Fe is also Dao, which is stable, making it less prone to being reduced compared to Ma. And vanadium's low value relates to the stability of Vra in certain environments.
So these potentials are really windows into the redox chemistry and stability. Now, achieving those really high oxidation states, you mentioned fluorine and oxygen, helps stabilize them.
Yes, they are the champions of stabilizing high oxidation states.
Why them specifically?
Fluorine is the most electronegative element and forms very strong bonds, or helps create stable crystal lattices with high lattice energy. Oxygen is also very electronegative and has the fantastic ability to form multiple bonds, double bonds, with the metal.
Can you give some examples?
Sure, we see high states in fluorides like titanium tetrafluoride, TiFu, vanadium pentafluoride, the F way, even chromium hexafluoride, CrF way. And with oxygen, you can get manganese heptoxide, MnEuros, or oxidations like vanadyl, VO, or permanganate, manganese +7.
And sometimes oxygen can achieve even higher states than fluorine can.
Yes, like in MnAers compared to manganese's highest stable fluoride, MnFu, that multiple bonding ability of oxygen is often the key.
Okay, so overall chemical reactivity, how does it vary? Are they all super reactive?
Not at all, it's quite a range. Many are reactive enough to dissolve in acids, but some are quite noble, like gold and platinum, resistant to simple acids.
What about the first row, the third elements?
Generally, they are relatively reactive, mostly more so than the heavier elements in their groups. Most, except copper, can technically be oxidized by 1-SO, meaning they should react with acid.
But sometimes they don't seem to react quickly.
Right. Kinetics can be slow. Sometimes a protective oxide layer forms, making them passive, like titanium and vanadium in some conditions.
And we saw the EO values show a decreasing tendency to form MR ions across the series.
Correct. And the MRI values tell us that ions like Mu and Co are strong oxidizing agents in water.
While others are reducing agents.
Yes, TO, VO, and CO are strong reducing agents. They readily give up electrons. CO is reducing because it wants to get to the more stable DO state in an octahedral field, while MO is oxidizing because it wants to get to the stable DO state. Stability drives reactivity.
That contrast is really clear. Okay, another big topic, magnetism. Why are so many transition metal compounds magnetic?
It comes down to unpaired electrons. If a metal ion has one or more electrons sitting alone in d orbitals, it will typically be paramagnetic.
Paramagnetic means attracted to a magnetic field.
Yes, attracted weakly. Diamagnetic substances have all electrons paired and are weakly repelled. Ferromagnetism, like in iron, is a much stronger cooperative effect, essentially extreme paramagnetism.
And can we predict how magnetic they'll be?
For the first transition series, often we can get a good estimate using the spin-only formula, which just depends on the number of unpaired electrons. N, it's U men plus 2 Bohr magnetons.
So measuring the magnetic moment can tell you how many unpaired electrons there are.
Exactly. It's a useful tool for figuring out the electron configuration and sometimes even the structure of a complex.
Cool. And related to those d electrons are the colors. Why are so many transition metal solutions and compounds colored?
That's another fantastic consequence of having partially filled d orbitals.
How does it work?
In many transition metal complexes, the d orbitals aren't all at the same energy level. They split into groups with slightly different energies. An electron can absorb energy from visible light and jump from a lower energy d orbital to a higher energy one.
An oddity transition.
Precisely. The energy of the light absorbed corresponds to a specific color. The color we see is the complementary color, the light that wasn't absorbed.
So the color depends on the energy gap between the d orbitals.
Yes, and that energy gap can be influenced by several factors, including the identity of the metal ion, its oxidation state, and crucially, the nature of the ligands attached to it.
Ah, so changing the ligand can change the color.
Absolutely. A classic example is aqueous copper sulfate, which is blue due to copper ions surrounded by water ligands. If you add ammonia, the ligands change, the energy gap changes, and the color deepens to a dark blue-violet.
That explains a lot. And this ability to interact with ligands leads to another key feature, forming complex compounds.
They are masters of coordination chemistry. They form a vast number of complex ions and compounds.
Why are you so good at it?
Several reasons. They're relatively small ionic size, they're often high positive charges, and critically, the availability of those empty or partially filled orbitals that can accept electron pairs from ligands to form coordinate bonds.
Makes sense. They have the charge and the orbital parking spots for ligands, and this ties into their catalytic properties too, doesn't it?
Very much so. Transition metals and their compounds are incredibly important catalysts.
Why are they effective catalysts?
Two main reasons link back to what we've discussed. Their ability to adopt multiple oxidation states and their ability to form complexes with reactants.
How does that help speed up reactions?
They can provide a surface or a site for reactants to bind, increasing local concentration and weakening bonds within the reactant molecules. They can also offer a lower energy reaction pathway by temporarily changing their oxidation state, essentially acting as electron relays.
Can you give some big industrial examples?
Sure. Vanadium V oxide, V-oro in the contact process for sulfuric acid, finely divided iron in the Haber process for ammonia synthesis, nickel for catalytic hydrogenation of oils. The list goes on and on.
They really are chemical matchmakers.
A great analogy. They bring reactants together, lower the energy barrier, and let the reaction happen much faster, often regenerating themselves at the end of the cycle.
Amazing. Okay, two more quick D block properties before we move on. Interstitial compounds, what are those?
These form when small nonmetal atoms like hydrogen, carbon, or nitrogen get trapped within the empty spaces or interstices of the metal's crystal lattice structure.
Trapped inside the metal structure.
Yep. They're often non-stoichiometric, meaning the ratio of metal to nonmetal isn't fixed. Think TiC, MEN, Figgy, or even things like VHA.
And what are these compounds like?
They tend to be very hard, have extremely high melting points, often higher than the pure metal. They usually retain metallic conductivity, but they become chemically much less reactive, almost inert.
Interesting combination of properties.
Yeah.
And finally, alloys.
Right. Transition metals are fantastic at forming alloys mixtures of metals. Because their atomic radii are often quite similar, they can readily substitute for each other in crystal lattices to form solid solutions.
And these alloys have useful properties.
Definitely. Alloys are often harder and have higher melting points than the individual component metals. Think of steel's alloys of iron with elements like chromium, vanadium, tungsten, molybdenum, manganese, or brass, copper and zinc, bronze, copper and tin. They're everywhere.
Okay, that covers a huge amount on the D block. Let's switch gears now to the F block, the inner transition metals. Where do they fit in?
These are the two rows usually shown separately at the bottom of the main periodic table.
The lanthanoids and actinoids.
Exactly. They're characterized by the filling of the 4f orbitals, lanthanoids, and the 5 orbitals, actinoids. Each series has 14 elements.
And they follow lanthanum, Le, and actinium.
Ain't hairy. Correct. Which is why Le and Ac themselves, although technically D block, are often discussed alongside them due to their strong similarities to the subsequent F block elements. We often use Ln as a general symbol for lanthanoids.
And you mentioned earlier the lanthanoids are known for being very similar to each other chemically.
Extremely similar, especially in their dominant +3 oxidation state. This makes them a fantastic case study for observing the subtle effects of just changing nuclear charge and size across a series.
Whereas the actinoids are more complex.
Much more complex. They show a wider range of oxidation states, and of course they are all radioactive, which adds significant challenges to studying their chemistry.
Let's tackle the lanthanoids first. Electron configurations.
They generally have a 6-ephes outer configuration, with the 4 orbitals being progressively filled across the series, but the key thing for their chemistry is the trivalent ion, LNO.
Their most stable form.
Yes. And these Ln ions have a simple configuration of 4-Phi, where LNO goes from 1 for cerium-3 up to 14 for lutetium.
And we already discussed the lanthanoid contraction impacting the D block, but it's obviously a defining feature of the lanthanoids themselves.
Absolutely. It's that gradual decrease in atomic and ionic radii from lanthanum across to lutetium.
Caused by the poor shielding of 4f electrons.
Exactly. As the nuclear charge increases, it pulls the electrons in more effectively, causing the shrinkage. The decrease is particularly smooth for the LNO ions.
What about oxidation states besides +3? Are there any?
While +3 dominates, some lanthanoids can show +2 or +4 states, particularly if doing so results in an empty, half-filled, or completely filled subshell.
Ah, that stability argument again. Examples.
Cerium can form cero configuration, but it's a strong oxidizing agent wanting to go back to cero. Europium forms Euphe, which is a strong reducing agent. Ytterbium forms YbFo, also a reducing agent. Terbium can form TiBo, an oxidizing agent. Samarium shows both cero and cero.
So exceptions exist but tie into electron stability. What are their general properties like?
They're typically silvery white, relatively soft metals that tarnish in air. Hardness generally increases across the series. Samarium is quite hard, like steel.
The melting points.
Mostly in the 1,000–1,200 Kelvin range, though samarium melts significantly higher. They're good conductors, typical metals. Density and other properties generally change smoothly, except for europium and ytterbium, which show some anomalies, likely due to their tendency towards the +2 state influencing metallic bonding.
Are they colored or magnetic?
Many of the alone ions are colored due to S-null electron transitions. These transitions give characteristically sharp absorption bands, unlike the broader dia-D bands, and most are paramagnetic unless they have an A or a FuO configuration.
What about reactivity?
The earlier members are quite reactive, chemically similar to calcium. The later ones are a bit less reactive, more like aluminum. They react with hydrogen, carbon, acids, halogens, oxygen, forming predictable compounds like LNOA oxides and LNOH hydroxides, which are basic. Their electrode potentials, LNO8ON, are quite negative, around 92.2 to -2.4 volts, similar to reactive metals.
Do they have many practical uses?
Yes, quite a few important ones. They're used in alloy steels for strength. Mish metal, which is mostly lanthanoids, is used in lighter flints. Their oxides are used as catalysts in petroleum cracking, and specific compounds are vital as phosphors in TVs and lighting for generating specific colors.
Okay, interesting stuff. Now let's move to the actinoids, electron configurations compared to lanthanoids.
They also have a 7 seconds outer configuration with variable occupancy of the 5 and 6-spin orbitals. The 5F orbitals are progressively filled, starting properly from protactinium.
Similar irregularities for stability.
Yes, you see configurations like americium having 5 Cera 7 Cetus and curium having 5 Fav 60 Eson 7 Cetus, aiming for that half-filled subshell stability.
But a key difference is the 5 electrons participate more in bonding.
That's crucial. The 5-ic orbitals are spatially more extended, less buried than the 4f orbitals. So they are more available to get involved in chemical bonding, which contributes to the wider range of oxidation states seen in actinoids compared to lanthanoids.
And they have their own contraction, actinoid contraction.
Yes, a similar gradual decrease in atomic and ionic size across the series.
Is it stronger or weaker than the lanthanoid one?
It's actually somewhat greater element to element than the lanthanoid contraction. The 5 electrons provide even poorer shielding than the 4f electrons.
Okay, oxidation states, you said a wider range.
Definitely. While +3 is common, especially later in the series, the earlier actinoids show a remarkable variety. Thorium is often +4, protactinium +5, uranium +6, neptunium even up to +7. This variety arises because the 5, 6, and 7's energy levels are very close, allowing different numbers of electrons to participate.
So their chemistry is more varied and complex.
Yes, much more so than the lanthanoids. It's harder to draw simple parallels across the series due to the changing oxidation state preferences. Their +3 and +4 ions also tend to hydrolyze readily in water.
What about their general characteristics? Appearance, reactivity?
They are silvery metals, but exhibit more structural variety than lanthanoids. They are highly reactive metals, especially when finely divided. They react with boiling water. Most nonmetals are attacked by HCl, but can be passivated by nitric acid. They don't react with alkalis, and of course, they are all radioactive.
Radioactivity is the defining feature, really.
It is. The early members, like thorium and uranium, have long half-lives, making them naturally occurring and usable. Later members have much shorter half-lives and have to be synthesized.
Magnetic properties, ionization energies.
Magnetic properties are more complex than for lanthanoids, harder to interpret simply. Ionization enthalpies for the early actinoids are generally lower than for the early lanthanoids. Those 5 electrons are less tightly held due to poorer shielding.
Do they become more lanthanoid-like later in the series?
Yes, the similarities increase in the second half, where the +3 state becomes more dominant. And the actinoid contraction, like the lanthanoid one, has consequences for the elements that follow in the periodic table.
And their main uses relate to that radioactivity.
Primarily, yes. Thorium and uranium in particular are key sources of nuclear energy. Plutonium is also important in this context.
We've covered a lot of ground, from the heart of the periodic table right down to the bottom rows. What are the main things you want listeners to take away from this deep dive into the D and F blocks?
I think the biggest takeaway is how these elements' unique electron structures filling those inner D and F orbitals lead to such a fascinating suite of properties.
Yeah.
Variable excitation states, color, magnetism, catalysis.
And those contractions.
And the contractions, yes. These aren't just abstract concepts. They explain why these elements and their compounds are so vital in everything from materials science and industrial chemistry to, well, nuclear technology.
And here's something to think about. It's amazing how these subtle differences in where electrons sit deep inside the atom result in things we see and use every day. The steel in bridges, the catalysts making plastics, the phosphors in screens, the fuel in power plants. These elements are doing critical work. It makes you wonder, what else could they do? What future technologies might depend on harnessing their unique properties in new ways?
That's a great thought to leave with. So maybe next time you look at a periodic table, give a little nod to those middle blocks and the rows at the bottom. There's a huge amount of complex and useful chemistry packed in there. Hopefully this discussion has maybe sparked some curiosity for you to look into some of these elements or their applications a bit more.